I'd like to talk to you about age of the Earth, and I'll try and do it in a lighter format so you can understand a little bit about my views of radioisotope dating. Grand Canyon, the inside story of the ground beneath our feet. You look around the Earth and you see evidences of the historical operation of process on the Earth. What formed the Earth? How did it form? When did it form? All kinds of questions come to our mind. How did those fossils get buried in there? What's that river doing in the canyon? All kinds of erosional forms and things like that. You might have detected from my previous discussion about Mount St. Helens that I have not always been a creationist. In fact, I was an evolutionist in my way of thinking about the Earth originally. Why did I once believe in an old Earth? I tried to put down the 5 things that convinced me of an old Earth. Laminated sedimentary rocks, things that seem to be deposited very slowly. Fine grain, textures, things like that. Large canyons with small rivers. Grand Canyon being one of the largest canyons I know, and it has a river down in the bottom, Colorado River. Petrified forests, the idea of succession of forests. Coal beds deposited in peat swamps, and radioisotope dating. Those are the primary evidences for why I once believed the Earth was old. Do you want to know what my primary evidence is for why I believe the Earth is young? Those. The same ones, okay? And that is interesting, isn't it? Okay, I investigated the processes and the products that used to convince me the Earth was old, and I started learning more about it, and it started to convince me the Earth was young, and so that's interesting. So laminated sedimentary rocks, I thought they were formed by the seasonal alternations between summer and winters, between wet years and dry years, and the boundary between adjacent thin sedimentary units represented long periods, sometimes nothing happening, long periods of inactivity. I've been reinterpreting that at Mount St. Helens in terms of rapid sedimentary process. I've kind of specialized in rapid granular flow of materials and discovered that the shearing action when grains flow over a surface segregates them by size, by shape, by their density, and creates laminated sedimentary deposits rapidly. And it's interesting to go look at the laminated sedimentary structures in the Earth's crust in terms of what we have seen in the laboratory, in flumes, and also what we've seen at Mount St. Helens, a natural catastrophic process. Large canyon with big rivers used to convince me of long periods of time. And when I first saw the Grand Canyon, I was thinking in terms of long ages and slow process. Did the Colorado River cut Grand Canyon? As I studied that issue, and most geologists have generally gone along with this, it doesn't appear that there's a 70 million year record of erosion of the Colorado River in Grand Canyon. There appears to be some kind of abrupt, almost instantaneous event that positioned the Colorado River through the upwarp plateau in northern Arizona. And it leaves open a young Earth interpretation. And the small river in the big canyon, it doesn't look like it was a little water over a long time. It looks like a lot of water over a little time. And those petrified forests, like at Yellowstone, used to convince me of successive forests. I used to think in terms of each forest level representing, or each level with petrified logs representing an individual forest. And as I explained earlier, the succession of forests, supposedly 27 distinct forests at Yellowstone, was evidence of tens of thousands of years of repeated forest growth, one on another. These forests grew, then soil developed, then another soil formed after a forest was buried, and then a second forest grew, and that whole thing happened repeatedly. And that could require multiplied thousands and thousands of years, the whole succession of strata, perhaps 40 million years in duration. We have seen at Mount St. Helens a miniature laboratory for the study of deposition of petrified forests and the way the logs float in Spirit Lake. 1 million logs landed in Spirit Lake after the eruption due to that giant water wave, and those logs have been floating around in that lake now for 23 years. I've been able to watch how the logs float and how they sink to the bottom of the lake. And one of the amazing things that we've discovered is that the logs in Spirit Lake float in upright position, and then as they sink to the bottom, they can stand on the bottom and get buried in vertical position, having the appearance of being a forest, part of a forest, a tree that grew in place. And so that's very interesting. And as we did the sonar survey there at Mount St. Helens, we discovered something like 20,000 upright objects on the bottom of the lake. And what would Spirit Lake look like if you drained it? It would look like a forest that grew there. But it's not a forest that grew there, it's a transported forest or a replanted forest on the bottom of this lake. And the whole configuration there suggests that there's some other explanation perhaps for the petrified forests at Yellowstone. And so that's interesting to see the process. And we looked critically at the Yellowstone petrified forests, and some of the so-called evidences of rooting in place of those petrified stumps, especially the vertical ones, aren't as strong as we thought they were. And the soil zones between the layers doesn't appear to be soils. And some of the tree rings seem to correlate on different levels, suggesting that forests where their root ends buried at different levels grew at the same time, falsifying the petrified forest interpretation. So petrified forests don't appear to be a conclusive argument for great age of strata. And then coal beds deposited in peat swamps. I told the story of the of coal beds, especially Kentucky coal study I've done, and thinking about floating log mat model for the origin of coal. And then seeing Mount St. Helens produce a log mat and all kinds of accumulation of broken plant material on the bottom of the lake, especially a peat layer up to 3 feet thick with sheets of tree bark abundant in the peat, having the appearance, if it was compacted and altered, of some of the coal beds we see in Kentucky and in the eastern United States. So coal beds deposited in peat swamps maybe need to be reinterpreted, and maybe not a swamp at all, but maybe underneath a floating log mat. So a log mat model for the origin of coal could happen rapidly, such as the peat accumulated at Mount St. Helens. And then the final one is radioisotope dating. And that's the one that the RATE project is attempting to address. And that was the one of the 5 that used to convince me the Earth was old. And I'll tell you that story. I'm going to talk about the radioisotope story. I've talked about the first 4, so now we can talk about this last one, radioisotope dating. Just a story. Okay, and it's late, and let me give you this story. It's kind of a lighthearted story, and it'll help you understand the nature of assumptions. They get involved in the way we think about the age of things. One day there were 2 space travelers that came from a distant planet. They came to Earth, and the purpose of these space travelers, of all things, was to understand the average age of a high school student, believe it or not. And they came to 2 different high schools, one here in Indiana, let's say, and one in California. And their purpose was to determine the average age of a high school student using scientific methodology. So our friendly space travelers landed here in Indiana, and what did they do? They measured the heights of high school students. And they measured hundreds of high school students, and they found that the average high school student is 65 inches high. And over the 3 years that they were measuring high school students, they discovered that the average high school student gains 1 inch per year. So how old does the average high school student appear on the basis of their height and their height gain? 65 inches high, and they gain 1 inch a year, would appear to be 65 years old. Well, our friendly space travelers who landed in California, they studied the California students, and they discovered the average high school student weighs 130 pounds, and after measuring hundreds of high school students, they discovered the average high school student gains 2 pounds per year over the 3-year period they measured high school students. So how old does the average high school student appear on the basis of their weight gain? They weigh 130 pounds on the average and they gain 2 pounds per year. How old does the average high school student appear on the basis of their height and their weight gain? Okay, good. You guys are really on to that. Okay, so our friendly space travelers got together here and started thinking about this. The average height is 65 inches. The height gain is 1 inch per year. The average weight gain is 2 pounds, 130 pounds is the average weight. Conclusion, the average high school student is 65 years old. Now, when they were doing this, the parents were there. What did the parents say? The parents gave eyewitness testimony that their students, their sons and daughters, were not 65 years old, but they were just teenagers. The eyewitness testimony conflicted. But our friendly space driver said, we just want the scientific evidence, you know, and so they concluded the average high school student is 65 years old. Okay, question is, what went wrong? What went wrong? Okay, think about it in our story here. Assumed constant rate. They extrapolated the weight and height gain over the life of the student. Teenagers are kind of unusual people, right? You don't want to extrapolate over their interval. Okay, assume zero initial condition. A baby, when it's born, has 0 height and weight. That's not a good assumption, is it? And they disregarded eyewitness testimony. They just wanted the scientific argument. Okay? Some things went wrong there, didn't it? Radioisotopes, similar. Here's some of those assumptions. Dr. Vardaman mentioned some of these. A closed system. We have an hourglass here with grains in the upper chamber and the lower chamber. We haven't removed or added any grains to the hourglass, if you will. The beginning quantities are known. We might assume that all of the grains were in the upper part of the hourglass as we begin, and there were no grains in the bottom of the hourglass, but that might not be the initial condition there. And constant rate of decay, or in the case of the hourglass, constant fall of grains through the apparatus. Those are some of the assumptions, and I think all of the assumptions can be questioned. And so that's what radioisotope work needs to be done. The Uncle Fred story. Okay, here's the Uncle Fred story to help you understand uranium-lead dating a little bit. A gift from your Uncle Fred on your birthday in the year AD 2003. You have a strange uncle, and he gives you a safe deposit box. Inside of there are 16 uranium atoms. Okay? Okay, now, what do you do with that? Uncle Fred gave that to you, and what are you going to do with your 16 uranium atoms? Well, you think about it a while, and they're radioactive, aren't they? Okay, and you just don't put that under your bed. You want to put it in a safe place. You think, where would be the safest place to put your safe deposit box? And after thinking about it, you say, the Federal Reserve Bank in Washington, D.C.? Well, anyway, according to the story, you put your safe deposit box in a safe place that will forever be there for you to observe. According to the theory of radioisotope decay, what will that box look like in the year 4,500,000,2003 AD? What would it look like? According to the theory of radioisotope decay, the present rate of decay of uranium-238 to lead-206, it should have 8 uranium atoms and 8 lead atoms. Okay, you see how that works? Okay, what would it look like in the year 9,000,000,000 2003 AD? you should have half of a half, or 4 uranium atoms, 12 lead atoms. And what would it look like in 13 billion, 500 million, 2003 AD? You should have 2 uranium atoms and 14 lead atoms. You see how that works? Half of a half over that decay period, or that what's called half-life. And so that's the kind of the interesting thing about the principle of radioisotope decay. Now let's say something, you lost track of what year it was that Uncle Fred gave you that gift. Okay, let's say you lost track of your birthday, what birthday Uncle Fred gave you that gift. Could you use his gift to tell time? Answer is yes, you could, couldn't you? So what you would do is, you stashed the gift back in the bank safe deposit box. You could go over there and look in the box and see what is the proportion of uranium to lead and get some idea of age. So you go over to the bank and you see this. You see 8 uranium atoms, 8 lead atoms. What do you suppose? You could calculate the age, 4.5 billion years, 1 half-life of uranium, say. That makes some assumptions that nobody's fiddled with your box, added or removed things, that there's been this constant rate of decay, and that we know what the initial condition was, that we all had uranium atoms to begin with. Okay, you kind of remember vaguely back there what that birthday was like, and you think there was 16 uranium atoms. Okay, well, the Uncle Fred story shows the nature of assumptions as they get involved and how you could use radioisotopes to tell time. Okay, important radioisotope pairs that you use to estimate age: uranium, lead. Uranium is the parent, lead is the daughter. Thorium is radioactive, giving another kind of lead. Potassium